morning, good evening everyone. So we'll be doing two awesome tests here as we continue these series tests. The alternating series test, and we'll also be doing the ratio test. So with this alternating series test, that series, we start at 1, starts at 0, whatever it is, you'll notice that, or maybe -1 to an m plus 1, or maybe a -1 to the n minus 1. One of these things you'll see in a series, that's going to make the series alternate. I'm going to put this on all three of these. That's what you need to focus on so that you know that, hey, perhaps, I'll say the word, perhaps we can use the alternating series test. Because this is what makes sequences alternate. And then maybe over here it has, 2 to the nth over n cubed, or n plus 5 over n plus 2, something extra. But I wanted you to realize, let's make an series alternate. It could be anything like this. -1 to the n minus 1, -1 to the n plus 1, or maybe just -1 to the n. And that's what we call an alternating series. And yeah, I guess you're saying, we're thinking, if I see this in a series, I guess I can always use the alternating series test. Not exactly, because this test, I want to emphasize one thing, it only shows convergence. So it's not like many of these tests we've done, like the geometric series test, where it has this, it converges, this, it diverges. Integral test. In this scenario, it converges, in this scenario, it diverges. This test is only used to show convergence. So if we don't have a proper setup, then we'll just go to something else. And I'll explain exactly what you probably want to go to. We'll talk about that. So this is what will make it alternate, but you may have stuff like, oh gosh, it could be just, here's something like, let's say we have a 1 over 2m plus 1 in the book here. I see when I'll do 5m plus 3, or the 6m plus 1. So about n cubed. These are just 3 examples of the kind of stuff we'll see. But maybe we can use alternating series tests like this. So what has to hold? 2 things. First of all, we got to make sure that the terms of the sequence decrease. That's the first check. We got to make sure that the terms of the sequence do decrease as n approaches infinity. So when we write this stuff, do you remember every time I wrote a sequence, I referred to a sequence as a sub n, the sequence portion? So let's refer to like all this here as a sub n. But the portion after that -1 to the n minus 1, that 1 over 2n plus 1, let's refer to that as b sub n. So that we're organized when we're doing this test. So this 1 over the 2n plus 1 will be b sub n, but a sub n will also include the -1 to the n minus 1. So same thing here. All this will be a sub n, but let's refer to b sub n as the 5n plus 3 over 6n plus 1. Or in this example, all this right here, we'll think of the sequence as a sub n, but just the n cubed over 3 to the nth we'll refer to as b sub n. Cool. And the 2 things, this is a great test, because you're pretty sure you're going to try it every time you see a -1 to the nth or -1 to the n plus 1. 2 things have to hold, the terms have to decrease as n approaches infinity, and then the limit of b sub n just has to equal 0. And that's it. It's a pretty cool test to try, but if the limit's not equal to 0, we can't use it. See, that's what's going on. You'll see a lot of these, the terms are going to decrease. So let's look at this one right here. We'll start with this one. -1 to the n minus 1 times 1 over 2n plus 1. And it's kind of like number 5 from the textbook. Do the terms decrease? Are the terms of b sub n decreasing? I say yes. Do you agree? 1 over 2 times 1 plus 1 Then you put 1 over 2 times 2 plus 1, 1 over 2 times 3 plus 1. What are those terms? You can just look at them. It'd be 1 over 3. What would be the next one? What are you plugging it to? 1/5. 1/5. Aren't they getting smaller? So that holds true. But we do have to make sure the terms are decreasing. Now, what's the limit as n approaches infinity of 1 over 2, which we're referring to as B sub n. You know, in terms of B sub n. So what's the limit of this? Notice I'm not doing a -1 here. I'm only focusing on B sub n. Isn't that funny about this test? We focus on B sub n every time. Is that 0? So this series right here converges by alternating series. This series converges by the, we can abbreviate, how about AST? By the alternating series. That's number 1. Great test, though. Converges by the alternating series. Have a look at that? Try the second one. You put yourself in test mode too. You're like, aha, you spot this. Of all the tests, geometric series tests, integral tests, the comparison tests, what's going to stick in your mind? Try what? Try it first because you see -1 to the end. Try the alternating series test. Give it a shot. If it doesn't work, we'll go to something else. Sound good? Let's focus on part 2. You know, I know the terms have to decrease, but what is the limit of B sub n? Before you just automatically think the limit's always 0, oh, converges by alternating series test. Everyone, I'm going to write this down. What's the limit as n approaches infinity of the B sub n? Just this part. You can think of the horizontal asymptote that exists, of that rational expression there. Or you can do L'Hopital's rule. What would be the derivative of the top? 5. What's the derivative of the bottom? 6. So what's the limit? Is it 0? That's not 0, is it? Right away, can we use the alternating series test? No, we just can't use it. I mean, here's my worst fear on a test. The student goes, diverges by alternating series test. You can imagine how many times I've gotten that. Alternating series test does not show divergence. There's no divergence test. And that's why on this summary sheet, I want to point out, you see this big X I have down here? I put a gigantic X, so you're reminded that, oh, it doesn't have a divergence test. So we're going to have to go somewhere else. That's okay. Alternating series test isn't telling us whether this converges or diverges. But you know where I want you to go? If this limit's not equal to 0, I always want you to go to this test. Because I believe you'll be fine. If you try alternating series test on -1 here, in terms of this sequence here, and we see we can't use it when the limit's not equal to 0, right? Then look at test for divergence. Go right to that. So I'll erase this. I can't use alternating series test. But what's going on by test for divergence? Now, test for divergence, I have to think of the entire sequence. Well, one of the coolest tests, remember what that says? If the limit of this entire expression right here is not equal to 0, or does not exist, then this series has to diverge. So is the limit of this expression right here with the -1 end, is it equal to 0? No, it's bebopping between a -5/6 and a 5/6. But it does not exist. So this series diverges by test for divergence. And I'll write that down. But I want to be clear. So if you try alternating series test, you notice you can't use it because the limit's not equal to 0. Go right to limit test for divergence. Go right to that. So I'm going to say that this series diverges by test for divergence. And then no, I have to somehow justify what test for divergence is, right? So let me just, it doesn't take much room here though. Because the limit as n approaches infinity. Now notice with test for divergence, I have to think of the entire A sub n. Okay? All this. And 5n plus 3 over 6m plus 1 does not exist. I look at DNAs. I'm worried that you look at that, might say 1, so I'm going to write does not exist. Does not The reason it doesn't exist, everyone, I know this was going to 5, 6, but the negative on the end is making it alternate between a negative 5, 6 and a positive 5, 6. A negative 5, 6 and a positive 5, 6. It's not converging to a number in terms of that sequence. But the limit is just non-existent. I'll get out of the way, I know why you're copying. So I hope you love this test. You know when you're going to try it, right? You know when you're going to try the alternating series test, but if it doesn't rule, it doesn't work, go right to test for divergence. Go right here, go, hey, I'm going to try test for divergence. That's what you do. Hey, try this one. N cubed over 3dn. Well, are the terms decreasing? Let's check it out. Are the terms of, remember I call this B sub n, here, your B sub n. Are the terms of B sub n decreasing? You just got to make sure that's happening. What's the first number? 1 cubed over 3 to the 1 is what? 1/3. Now plug in a 2, what do you get? You get 8 over, what's 3 squared?
9.
And now, and I chose this problem on purpose, you may be freaking out like we can't use this test. Because those numbers decrease. I know you're sitting there going, I don't know if I can use this. Did those decrease? No, so let me be clear about this. I know that this theorem, or excuse me, this series test says the terms of B sub n decrease as n approaches infinity. What we mean is this. Would you put this down in your notes? That it eventually decreases. That it eventually decreases. You could have a little split at the beginning, a couple numbers where it actually jumped up. Do you notice that went up? That number's higher than that. But let's look, a few more. This was n equal to 1. This was the second term. What's the third term of B sub n? 27 over 27. All right, 1. What's n into 4? 64 over what? Aha. Do you see what's happening? Now they're starting to go down. Try n to the fifth. Or n equal to 5, the fifth term. 125 over 3 to the fifth. 243?
Yeah.
And when these are starting to decrease after the 1, 2, 3, after the third term. So these terms do decrease eventually. And you can keep going. What's the next number going to be? It'll be the sixth term. Well,
16.
you want to try it out? What's 6 cubed? 216? What's 3 to the 6th?
729.
See what's happening? They eventually decrease. So don't let that throw you off. I didn't want you, because I think it happens, everyone, on number 11 in the homework, in the practice problems, where maybe the first 2 terms it actually went up a little bit, like here. Increase, but eventually it what? Eventually starts decreasing. So I'll make a note that these terms are decreasing after which term? After the third term. Jessica?
What point do we stop trying to see if the equation will override that decrease?
I would say when you examine these, if you didn't see it after like the first 5 terms, yeah, that would be it. See, notice here it was right away. Right, that's what, 0.3? The line, that's 0.2. But in some cases, I didn't want that to startle you. You're like, they're not decreasing. But these usually go hand in hand. When the terms are decreasing, these usually go hand in hand. You'll notice that the limit of the sequence is 0. Okay, so they usually go together. I can see someone going home tonight practicing this and giving up on a problem because look what they observed right here. They went up, but they eventually will decrease. That's the key, eventually. All right, so I'm going to write this down. It started decreasing after which term? After the fourth term and beyond? All right, so I'll put n equals 4 and higher. Terms of B sub n decrease for the fourth term and beyond, right? I can use n equals 4 because we've got these n's in here. And what's the limit? I know you know this one. The limit as n approaches infinity. And when I got a monomial, n cubed over an exponential.
0.
Right? Who wins that race? Who increases more rapidly? Exponential, right? Right? Nothing beats exponential except for factorial. We were talking about L'Hopital's rule a few minutes ago. Could you do L'Hopital's rule if that bugged you? You sure? Again, what's the derivative of 3n cubed? 3n squared. This derivative, you may not know, we're so used to e to the x. What's the derivative of e to the x? E to the x? Well, 3 to an x, the derivative is 3 to the x times natural log of 3. But still, you could keep doing that. You'd see eventually that this right here, the limit is equal to 0. So in this series, converges by what test? AST converges by AST. Ooh, you got it. It converges by AST. Awesome. Okay, I'm going to talk about this alternating series estimation theorem. There was a problem in the book, and I recall that this problem, I'll raise these. Is that okay? Yeah? Hey, if you don't see that limit going to 0, what test will you go to? For alternating series test. Now you see this in a series, or something like that in the series, and you notice the limit isn't to 0, go right to what test? TFD, test for divergence. All right. So and this is number 19. Alternating, right? N to the n. So look at that carefully. This is 22. This section's great. These problems go quick. We know what test we're going to try. My gosh. You don't have to do any crazy integrals. Is that n minus 1? Yeah, they got n minus 1. This one started at 1, and this one started at 1. We were just talking about this. N factorial increases so rapidly, right? We were talking about 10 factorial, and it's already humongous. Right? Your TI-84 calculators, try 70 factorial. It can't even show it. It's an overload. Did you know that? If you try to hit 70 factorial on those TI-84s, it's too big, right? But, what about n to the n? Who's increasing more rapidly? N to the n or n factorial? N to the n. So, we can't use the alternating series test. You know why? The limit's not equal to 0 b sub n. Does someone see that? But, what test can we use? Let's not say, oh, diverges by alternating series test. Let's go right to the what? Yep, test for divergence. So this series diverges by test for divergence. Maybe that TFD looks better. Because the limit, as n approaches infinity, now I got to include the entire a sub n, negative 1 to the n, times the n to the n, over n factorial, does not exist. If you wonder what it's doing, it's bebopping between positive and negative infinity. Right? It's divergent in terms of the sequence, but it's also making the series divergent. Isn't that cool? Was that okay with that? Oh, let me go the other way, Juliet.
Thanks.
You bet. So right away, do not write, oh, diverges by alternating series test. It only shows one. Convergence. But go right to the test for divergence. This is the one I wanted to make sure to do with you, everyone, because a lot of times on an exam, I have students who look at this and they think it's geometric. And they're going through their list and they're like, let me just do a geometric series test on this. Is this geometric? This is not a geometric series. If that n wasn't there, yes it is. If that n was not there, you got everything exponential. Does anyone see that? But you got an n over 8 to the n. This is not geometric. So let's definitely try this what? Alternating series test. Well, first of all, do the terms decrease? Are the terms of v sub n, the v sub n terms decreasing? Or eventually decreasing? Are they eventually decreasing? Let's check it out. What's 1 over 8 to the 1? All right. Remember, I'm just looking in terms of v sub n. This is the v sub n right here. What happens when you put a 2 in there? Oh, yeah. They're shrinking, right? Check. V sub n terms are decreasing. Jessica, okay with that? I just noticed the first 2. It's going to continue. Because you plug in, what's the next number? 3. And you got 8 cubed. What's 8 cubed? What's 64 times 8?
256.
64 times 8. Is that 512?
512.
Yeah. I mean, they're just shrinking. And what's the limit? As n approaches infinity, of an n over 8 to the n.
0.
It's 1 to 0. Exponential blowing away that polynomial on the numerator. Or do L'Hopital's rule, the derivative, this is 1. What's the derivative of 8 to the n? Natural log of 8 times 8 to the n, which is still setting that thing equals 0. So this converges by what?
AST.
AST. Ooh. Hey, now we're going to do the alternating series estimation theorem. This theorem is really cool. This is an awesome theorem because now we can estimate. Have you noticed we've been trying to estimate these series lately with the integral test? The only test that gives us an exact value is the geometric series test so far, right? Well, we can estimate how accurate it is in terms of how close is it to, you know, can we have it accurate to 4 decimal places, 5 decimal places? With these calculators, sometimes you can get it accurate to 8, 9 decimal places in terms of what you have there. All right, so what's it say? For this alternating series estimation theorem, over there I have something like this. R sub n with the absolute value bars over it, less than or equal to b sub n plus 1. This is an alternating series estimation theorem. What the heck does this mean? So, to better understand this, we'll work a problem. So I'm going to take number 23 from the textbook. And this is what it says. Got this series. N equals 1. We'll do a couple of these. N equals 1 to infinity. Negative 1 to the n plus 1. All over n to the 6th. All right. And they ask this question. Oh, well, hey, before I ask this question, could you do me a favor? Can you make sure that series converges? We would waste our time if the series doesn't converge, right? So can you just make sure that converges? Does that series converge? It does. See how quick you can see it? Are those terms decreasing 1 over n to the 6th? Yeah, they're getting smaller and smaller. What's the limit as n approaches infinity of 1 over n to the 6th? 0. So this series is converted by alternating series. But what we're asking here is, how many terms of the series do we need to add in order to find the sum accurate to and they gave an error? I'll write this down. How many terms of the series do we need to add in order to find the sum to the indicated accuracy? All right. This is the accuracy they wrote for number 23. 0.1, 2, 3, 4 zeros, and then a 5. Okay. And in front of this, they wrote, let's see, take that off here. They wrote the bars around the theorem. Less than. Double check with Chris.
about my eyes. That is 4 zeros and a 5, right?
Okay, good.
You got pilot eyes.
So we got 4 zeros and a 5. How many terms of the series do we have to add? So to get this thing started, we gotta start looking at all the terms. Like an n equals 1. And you can make a table. The first term, what's the a sub n? So when I'm gonna plug in a 1, what do you get? -1 to the 1 plus 1 is what? 1. What's 1 over n to this 1 to the 6th? 1. Okay. Go to the next term. 2. Eventually we're going to see how far we got to get. I plug in a 2 into this thing. If you want, everyone, you can just look at the absolute values because they're talking about the absolute value there. But even if I get positives and negatives, I'll change it to negatives and positives. Nothing wrong with that. What happens if you put a 2 in this? That'd be the first term. Does everyone agree? Be careful. Sometimes these start at a 0. Have you seen it? Sometimes the series start at a 0. I'm going to plug in a 0 first, but this started at a 1. All right, that's the first term. It's a 1. What's the second term?
-1 over 64.
-1 to the third, which is -1. And then 2 to the 6th is
64.
64. We're going to write this as a decimal, though. So, Isaac, what's -1 over 64? Keep in mind, we're just going to focus on the positive values. You can
0.01.
take the absolute value of this. Oh, what do you get?
0.015625.
0.015625. And it was negative, right? But I don't care if you kept that positive in terms of that. I'm going to keep it negative because eventually we're going to add these up. So think of the absolute value of that. Think of the absolute value of that number. Is the absolute value of that number less than this? No. So we got to keep going. We got to continue this. So now we notice this particular problem, I think the technology is going to make this stuff easier, right? If you want to just keep doing this by hand, you can. I'm going to pull up the screen and I'm going to use the list. If you want, you can look at the list and we'll do that. But everyone, I'm going to keep going until I get the number that's lower than what? This. That's what I'm going to do. It's pretty simple, isn't it? And then I'll be very precise in how we're going to answer this question. Because it's got a, doesn't say b sub n, it says b sub n plus 1 there. Does everyone see that? So if this was like 5, this would be a 5 plus 1, 6 term right there. So, let's continue, but I'm going to use technology. If everyone's okay with that. Okay if I pull it down? You sure? Thank you. Yeah, thank you. I'll pull it up. Now, I'm just going to continue this, but sometimes with those G83s and 84s, you may prefer to have it in a list. Right? So I'm going to use the calculator, put all this stuff in a list. Ooh, thank you. Thank you so much. Okay, so this is what I'm going to do. I'm going to go to just a list one. So I'm going to go to stat. I'll go to stat. And then I'll hit enter for edit. And now in L1, what I'm going to put in L1 is just the numbers. What is it? 1, 2, 3, 4, 5, 6, 7, 8. Just get it going. I could have gone further. I just want to see. I'm going to keep doing this until I get a number in the second column that's going to be lower than a number. So what am I going to type in the second column? I'll go over here, I'll right arrow. I'm going to up arrow into this L2 and I'm going to type, what's the formula? It's -1 to the n plus 1. Do I have to write that? I don't have to type that. I really just got to do the divided by the what? End of the 6. So that's what I'm going to type. I'm just going to hit 1 division, and then I'm going to hit that x variable raised to which power? Raised to the 6. And just do that. Oops. Yeah, I was thinking X because it's like a thing, it says L1 there. Thanks, Dave. I'll go back to stat edit. Yeah, edit. So funny, because so many times you'd be doing like, using Microsoft Excel. I'm gonna hit 1 division, and I'm gonna raise, is it X to the 6th or L1 to the 6th? L1 to the 6th. So how do I get L1? Second one. And just raise it to the 6th power. Just so you can see all these at once. All right. Which number is the first term to get lower than 0.0000? That's 4 zeros in a 5. Which one is it? It's the 6th term. Outstanding. And when they recognize it, it's going to be this number right here. That says 2.1 e to the negative 5. So in the 6th term, which was, look, no, 6, was 2.1 e negative 5. That means 2.1 times 10 to the negative 5th power, right? Which is, how many zeros in front of that 2?
4.
4 zeros, then a 2. I want to make sure one can see that. I'll just pop the light up real quick. Does everyone see when this is in scientific notation, how to convert it to a decimal? So this is the first term that's lower than this, right? Well, according to the remainder theorem, what we're going to do, hey, can you read those other numbers to me real quick? What were these other numbers? What was 3?
3 was
0.00,
1 through 7.
that'll work. Number 4th term,
2.4 e to the negative 4.
4, 5th term.
6.4 e negative 5.
All right. So this is what this theorem, this is awesome theorem, but this is what we do. We went through checking each number until we found the number that was lower than this value here, right? What was the first term that was lower than? Because the rest are going to be lower than it too. The first one was the 6th term. According to the theorem, what we need to do, we need to add the 1st through the 5th terms to obtain this accuracy. Let me be clear again. The 6th term was the first term that was lower than this, right? That means by this theorem, we have to add the first 5 terms to get the desired accuracy that we want. So the accuracy of adding up those 5 terms will give you an error less than or equal to this, to the actual sum of that series. So hey, I want to make sure we're clear on this. What if we did another problem and it took the 11th term? How many terms you got to add up? 10, the first 10. What if you did another problem and it was the 4th term? Then to get the desired accuracy, you got to add up the first 3 terms. Does everyone follow this? That's what they mean by this n and this n plus 1. Hey, one more, I think you got it. One more time. What if it was the